The last topic we're going to talk about in this chapter is about resonance and how resonance really kind of works. Now, when we talked about resonance initially, we talked about it as a collection of resonance structures, which we then combined to say, well, really what we have is a resonance hybrid, where that negative charge is shared by each one of those oxygens, in the case of nitrate. And we said this is what really exists, and these are some approximations that help us organize the information. So how do we use molecular orbital theory, or valence bond theory more specifically, to explain what's going on in resonance? How do we have electrons that aren't in one place, and where are they? How does that work? So in reality, what's going on in nitrate is if we think about the pi bond that we've got to make here, we don't have the nitrogen and one oxygen bound together in a pi bond, and then the next one, and then the next one. Really what we have is a system where our molecular orbital has this delocalized space for those electrons at all times. All right? So that set of electrons lives in these orbitals, right? It just sort of floats around and is an amount of electron density that is shared over that space. So we call being not localized or being delocalized. Right? A localized electron is always in the same place, kind of like the lone pairs that we have out here on this oxygen. They live there and they don't move around, right? They're attached to one atom. Or localized electrons might be the sigma bond between the nitrogen and the oxygen. Those electrons are localized, right? They're always in the same place. Delocalized electrons are going to be like these ones that are shared in that resonance system. So they sort of are shared over a broader area beyond one atom or the area between two atoms, right? So we're going to be shared over at least 3 atoms. Another really good example of this is benzene. Now benzene as an organic molecule is C6H6. And what we kind of don't see in this structure here are the hydrogens that are coming off of each of these vertices, which are representing a carbon. And we can see that we have 2 resonance structures where kind of all I do is I rotate these double bonds around the circle, right, which is sometimes why you'll see benzene drawn as a hexagon with a circle in the middle. It stands for that circle of dotted lines that we'd see in our resonance hybrid. So we have 2 different systems going on here in benzene. We've got our sigma system, where we see all of those localized electrons. All right, we see there's my hexagon, and then I have those bonds going out to the hydrogens from each of the carbons. And then we've got a pi system. All right, now our pi system is made up of a series of unhybridized p orbitals, and that's key that they're unhybridized, that share those electrons, right? In this case, 3 pairs of electrons are delocalized over those 6 bonds. What does that look like? It's going to look something like this, right? So if we think about these 2 structures as being kind of the resonance structures that I could draw, my hybrid gives us a good picture of what that delocalized system actually looks like, which is a ring of electron density above and below the plane of the molecule, which gives benzene a bunch of interesting properties like how it'll stack, how it solvates some things. We talk about this deeper as we go further and further into chemistry, but for today, we want to focus on the idea that this concept of putting these pi bonds together and delocalizing the electrons means that it's going to have a distinctly different behavior than if these electrons were always localized between 2 atoms. Right? Easiest one for us to talk about is something we discussed back when we introduced resonance. We don't have a long single bond and a short double bond. We don't see this alternating system of long and short bonds in benzene, right? We see equally sized bonds, right? I could make that even sort of more obvious here, right? We don't have long and short and long and short. Instead, we have our equally sized bonds all the way around, with those electrons delocalized over the entire ring. Again, where we get that circle from. Benzene, of course, isn't the only place that we see this, right? Benzene we've got above and below. Ozone, you might recall, our first example that we looked at in terms of resonance had the back and forth, which side is the double bond actually on? And in this case, we said, oh, really, it's going to be an average of the two. And what does our average look like? It looks like a place where I've got those two pairs of electrons delocalized over these two bonds. All right, being our, is it a lone pair? Is it a bond? Is it a lone pair? Is it a bond? So we've got those two pairs of electrons delocalized over those three atoms. That's really going to be it. That brings us to the end of chapter 11. Congratulations, you've made it through our final bonding theory for the course, and we'll continue to build on that as we move into chapter 12 and beyond. Chapter 12 is going to discuss intermolecular forces and how molecules stick to each other as opposed to how atoms stick to each other in molecules. So you can get ready for that, but rest secured in the knowledge that you're good up through how does this molecule work and what shape is it, and reflecting back on all the other things we had to teach, or learn rather, to get to this point. Congratulations, and I'll see you next time.